Can you see my screen?
Yes, ma'am.
Okay. Okay, so we saw a little bit about context-free grammar and what kind of languages are accepted by context-free grammars. And the ones which we saw were quite simple in structure. Now we will look at another example. It's a little bit more involved, and this is of balanced parentheses. So here is the problem. So you have an expression over the square brackets, or left and right square brackets, such that every left parenthesis is matched to a right parenthesis. This is the first condition. And secondly, the matched pairs have to be well nested. So this is in words. What I mean is there is an inductive definition where you start with these two brackets. This is the base case where you have just one pair of parentheses. This is the base case. And after that, inductively, you can say that if alpha is a balanced parentheses expression, then from this I can derive two kinds of inductive definitions. Okay, no, let me write two kinds of inductive definitions. The first one is if alpha is balanced parentheses, then so is left parentheses alpha, then right parentheses. And the second one is if alpha 1 and alpha 2 are balanced parentheses, then alpha 1 concatenated with alpha 2 is also a balanced parentheses. So this is the inductive definition for whatever I've said over here, that every left parenthesis should match a right parenthesis and it should be well nested. Okay, so any questions regarding the problem definition? Okay, so let's look at a few examples. For example, these are positive examples where you see over here, it's just a nesting of left and right parentheses. Here you have some concatenations. Here is a pair that is matched. Here is a bunch of, here is a substring where it is well nested. And then again, a pair that is well matched. So the concatenation of these three substrings forms another substring that is well nested and where every left parenthesis has a matching right parenthesis. Similarly, over here, you have two such substrings which are if you just take the two pairs themselves, they match each other. And then there is a substring where you have a well nesting. A slightly more complicated substring where you have a well nesting. But together, they again form another well nested expression of balanced parentheses. Now, here are some negative examples. So if you look over here, then you see that the number of left parentheses is more than the number of right parentheses. So the first condition does not hold for this string. And in the second string, the number of left parentheses is same as the number of right parentheses, but this is not well nested. If you look at these two parentheses, then they are in the opposite order. It's not a proper nesting. Okay, so given the inductive definition where I said that this is the base case, and then you have, if alpha was a balanced parentheses, then bracket alpha would also be a balanced parentheses, and if alpha 1 and alpha 2 were balanced parentheses, then alpha 1 concatenated with alpha 2 would also be a balanced parentheses expression. Intuitively, this seems to be a grammar that captures this structure. S, the productions will be S going to bracket, left bracket, S right bracket, or S going to SS, or S going to epsilon. But now we have to prove that this actually is a grammar for this particular language. Just as an example, if I want to derive, let's say, left bracket, right bracket, followed by another left and right bracket, then this is how I can do a derivation. You start from S, and then you use the production S going to SS. Now, you consider the first S that appears and replace it by left bracket, S, right bracket. Then again you consider this first S and you replace it by S going to epsilon. So you replace this S by epsilon. So you get a left bracket, right bracket followed by S. Next, you take this particular S and replace it by left bracket S right bracket. And finally, you take this S and replace it by epsilon to get this one left and right bracket followed by another pair like that. So this can be a derivation from this particular grammar. But this is one particular example. We need to make sure that any balanced parenthesis expression can be derived from this particular grammar. Only then can I say that the language corresponding to the balanced parenthesis expressions is a context-free language where this is the grammar for that language. Okay, so the objective now is to prove that this grammar is correct. Any questions so far? Okay. Let me go through just one more derivation. So if this is a two nested set of brackets, then you start with S, take the production S go into bracket S, then again take this particular S and take the same production S going to bracket S bracket. So you get this in the second step of derivation. Then again you take the S in the non-terminal symbol S. That's the only one in this expression, and you replace it by epsilon using the production S going to epsilon. So you finally get whatever you wanted to derive from starting from the start symbol S. Okay. So now let's look at, so we have an inductive definition. Let's look at another way of defining the same set of expressions, same set of strings over left bracket and right bracket. That will help us to prove that the given grammar, the grammar that we are suspecting is the grammar for this language, it will help us to prove that this is the correct grammar. So again, for a string x over left bracket and right bracket, I will define the function Lx to be the number of left brackets in x, number of left parentheses in x, and similarly Rx will denote the number of right parentheses in x. Now, this is a necessary condition, and later on, so I've put in an if and only if, because this will later on, you can show that it's also a sufficient condition. So a string will be, a string of parentheses will be balanced if Lx is equal to Rx. This is the first condition. And then the second condition is you take any prefix y of x, then the number of left parentheses in y is at least the number of right parentheses in y. So you take any prefix of y could be x itself, L of y is greater than equal to R of y. So a right parenthesis can only match to a left parenthesis to its left. This is basically what it means. This is, if this happens, then you can assure nesting. So if you notice this, you can also think of it, if you recall in the last tutorial, you looked at the surplus function. So if I think of S of y to be the surplus in terms of left parentheses and right parentheses, I can define the surplus function to be L of y minus R of y. And the claim is that it's going to be, y is going to be, or x is going to be balanced if and only if for all prefixes y, the surplus function for y is greater than equal to 0. Okay, so it's easy to see that these are necessary conditions, and for sufficiency, basically you try and show that look at the inductive definition. A string can look as follows. It could either be in the base case it could be like this, or it could be of the form some bracket alpha or alpha 1 alpha 2, and in all cases you try to show that if these conditions hold, that L of x is equal to R of x, and for every prefix L of y is greater than equal to R of y, then one of these three structures has to hold for that particular string. And like an intuition, I'm not giving you the full proof, but the intuition is you just look at the graph where it is x versus the surplus function Lx minus Rx. And every time you see a bracket, a new bracket, left bracket, you go one step up. And so after the first one, you go to 1. After seeing the second one, you go to 2. And then every time you see a right bracket, of course, the surplus is going down. So you keep moving downwards. And the mapping will basically be you take the position of the right bracket, you go upwards till you hit the graph, the curve of the graph. Then you go towards the right till you hit the curve of the graph again, and then you move downwards till you hit the x-axis. That you will find a left bracket at that point, and that is the matching bracket to the right bracket you wanted to match. But now, in order to prove this, so basically the surplus function, whenever the surplus function is positive, you will have the entire graph in the first quadrant. So you try to show that no matter what happens, if the two conditions hold, then these are the structures that are possible using this graph of surplus versus X itself. Okay, so now we will be working on these two conditions. We will say that a string is balanced if and only if L of x is equal to R of x, and if you take any prefix, then L of y is greater than equal to R of y, or that the surplus function for y is greater than equal to 0. So in particular, one way of showing it is any string that is, so we have to show, our ultimate goal is to show that the grammar that we have constructed, more or less by using the intuition of the inductive definition of the set of languages, any string that is generated by that is derived by that grammar should have these two conditions. So any string that is derived from that grammar should satisfy these two conditions: Lx equal to Rx and every prefix having positive surplus value. And any string that has that for which these two conditions hold must also be derivable from the grammar we have chosen. So let's get into that. Any questions so far? Okay, so this is the objective for the production. S go into bracket S bracket or SS or epsilon, where S is the start symbol, this single start symbol. We need to show that the given grammar is generating exactly the set of strings where strings which are balanced parentheses strings, and that basically means it satisfies the two conditions for balanced parentheses. So let's look at the first half of the proof. So let's look at a string X that is generated by, that is derived from S under this grammar G. And we want to prove that X satisfies the two conditions 1 and 2. So we will be inducting on the length of the derivation of X. In particular, we will actually be doing something more general. We will be looking at any string or any sentential form in N union sigma star. And we will show that any such sentential form that is derivable from S will be satisfying 1 and 2. Conditions 1 and 2. And therefore, we will actually be inducting on the length of the derivation of alpha. And in a special case, when alpha is a sentence, then we will have shown that any sentence that is derived from S also satisfies 1 and 2. So in the base case, in 0 steps, if S derives alpha, that means that alpha is equal to S, and then trivially the two conditions hold. There are no left and right brackets, there is only one non-terminal symbol, so trivially it holds. Okay, so now in the induction step, let's assume that you get S, you are deriving S, you're deriving alpha from S in, let's say, n plus 1 steps. So if I take one step back, that means S in n steps goes to beta. This beta could be S, this n could be 0. It goes to beta, and then beta in one step goes to alpha. beta in one step, it derives to alpha. So by induction hypothesis, notice that beta, the number of steps to derive beta is less than the number of steps to derive alpha. So by induction hypothesis, beta satisfies 1 and 2. Now let's concentrate on what happens in this one last step of derivation from beta to alpha. So there can be three types of productions that lead from that derives alpha from beta. So the first is S going to epsilon. So that means that beta is of the form some beta 1 S beta 2, beta 1 beta 2, at least one of them could be epsilon. And alpha, basically this S gets replaced by epsilon and alpha becomes beta 1 beta 2. But notice that this is just a non-terminal symbol being replaced by epsilon. So there is no change of order in the parentheses in beta 1 S beta 2. I mean, going from beta 1 S beta 2 to beta 1 beta 2, there is no change of order in the parentheses. I just replaced a non-terminal symbol that has nothing to do with left bracket or right bracket. I replaced that symbol by epsilon. So alpha will also satisfy 1 and 2 if beta was satisfying. Is this point clear? Any questions so far?
No, ma'am.
Okay. Does someone have a question? Okay. So again, the another production is S going to SS. Again, if we use this production, it means that I am going to replace a non-terminal symbol by two non-terminal symbols. So I'm not adding or subtracting. I'm not changing the order of parentheses. If so suppose over here instead of S, if I introduced SS, I will not be affecting the order of parentheses. So therefore, by a similar argument, if beta was satisfying 1 and 2, then alpha is also going to satisfy 1 and 2. Now the interesting case is what happens if I am introducing I am applying a production where I am introducing some new brackets. So in particular, the production S going to left bracket S right bracket. So then what does it mean? Beta will be of the form beta 1 S beta 2 and alpha will be of the form beta 1 left bracket S right bracket beta 2. And now we need to show that both conditions hold for alpha as well. So condition 1 is easy. L alpha is equal to L beta plus 1 just by definition. I have introduced one extra left bracket. And now by induction hypothesis for beta it is true that L beta is equal to R beta. So L beta plus 1 can be rewritten as R beta plus 1. And just if you look at beta and if you look at alpha, there's a difference of one right bracket. So therefore R beta plus 1 is equal to R alpha. And therefore for condition 1 holds. Now let's look at condition 2. Let's look at condition 2. I want to show that if you consider any prefix of alpha, then too the surplus function of that prefix should be positive, should be at least 0. Okay, so let's consider a prefix gamma and we know we are in the case where alpha is of the form beta 1 bracket S bracket beta 2. So gamma can be of three forms basically, depending on whether it's a prefix of beta 1 or beta 1 up to S or of the entire alpha. So firstly, if gamma is a prefix of beta 1, then it will be a prefix of beta as well, and therefore condition 2 will hold because the condition 2 holds for beta. Next is gamma is a prefix of beta 1 bracket S. So we have introduced an extra left bracket. But it's not a proper prefix of beta 1. There is something from bracket or S is included in gamma. So then if I look at the number of left brackets in gamma, it is definitely one more than the number of brackets in beta 1. So L gamma is equal to L beta 1 plus 1. Now, if you consider beta 1 is a prefix of beta. So therefore, by induction hypothesis, we know that the surplus for beta 1 will be greater than 0. greater than equal to 0. So I can replace L of beta 1. I can say that L of beta 1 plus 1 is greater than equal to R of beta 1 plus 1. Just applying induction hypothesis on beta and noticing that beta 1 is a prefix of beta. Now R of beta 1 plus 1 is obviously greater than equal to R of beta 1. And notice that the number of right brackets in beta 1 is same as the number of right brackets in any prefix of beta 1 left bracket S. So R of beta 1 can be written as R of gamma in this particular case when gamma is a prefix of beta 1 left bracket S. So therefore condition 2 still holds for any such gamma. The final case for gamma is
Ma'am,
a
can you explain
prefix
the last two steps from R of beta
here.
1 to R gamma?
Okay.
Yes, ma'am.
Okay, so over here we applied L of beta 1 is greater than equal to R of beta 1 by inducting on beta and noticing that beta 1 is a prefix of beta. Okay, so then L of beta 1 plus 1 is greater than R of beta 1, and this step is just R of beta 1 something plus 1 is greater than equal to something. R
Yes,
of
ma'am.
beta 1 plus 1 is greater than equal to R of beta 1. But now notice, look at beta 1 and look at gamma. Gamma is a prefix of beta 1 left bracket S. So notice that whatever is added after beta 1 does not have any right bracket. This is just one left bracket and one non-terminal symbol.
Okay, ma'am, got it.
Yeah,
Since
so therefore the number of right brackets in beta 1 is equal to the number of right brackets in gamma, no matter what gamma is. In this particular case, because gamma I am considering to be a prefix of beta 1 left bracket S, but not a prefix of beta 1. So it will contain something from left bracket and S. Okay?
okay,
Yeah. Okay, so final case for gamma is it is a prefix. It is of the form beta 1 left bracket S right bracket delta. Delta is a prefix of beta 2. Delta could be epsilon. So I'm taking just one case in this. Now again I have to compare L of gamma and R of gamma. So L of gamma can be written as L of, now notice this, I am considering the string beta 1 S delta. Okay, so L of beta 1 S delta plus 1. If you just consider the left bracket in beta 1, if you consider the left bracket in beta 1 S delta and beta 1 S delta, there is just one extra left bracket being added. So L of gamma can be written as L of beta 1 S delta plus 1. But beta 1 S delta is a prefix of beta, because beta was of the form beta 1 S beta 2 and alpha was of the form beta 1 bracket S beta 2. So beta 1 S delta is a prefix of beta. Therefore, I can rewrite L of beta 1 S delta plus 1 to be greater than equal to R of beta 1 S delta plus 1, inducting on beta.
Ma'am, can we call beta 1 as delta as a prefix?
Beta 1 S delta as a prefix of beta, not as a prefix of alpha, right?
But ma'am, in between we are skipping the left bracket.
Right. So this first step that we are taking, L of gamma, gamma is a prefix of alpha. Beta 1 S delta is a prefix of beta. I am just noticing this has nothing to do with prefixes. I am just saying, look at the structure of gamma, look at the structure of beta 1 S delta. Number of left brackets on the left hand side is one more than number of left brackets in beta 1 S delta. This is just structural information.
Yes, ma'am.
Right. Now this is a prefix of beta. This was a prefix of alpha. So if it's a prefix of beta, I can conclude something by induction hypothesis on beta, right? Because beta has less number of steps of derivation than alpha. So I am assuming that for beta, the induction hypothesis holds.
Yes, ma'am.
So beta 1 S delta is a prefix of beta. For beta conditions 1 and 2 hold. Therefore, for the for this particular prefix, it's true that the number of left brackets is at least as much as the number of right brackets. So I can replace this expression by greater than equal to number of right brackets in this prefix of beta plus 1. Now I come back again to the structure of beta 1 bracket S bracket delta and beta 1 S delta. Notice that if I just, so beta 1 bracket, this is equal to gamma. Just structurally, if you compare these two things, then the number of right brackets in this is 1 less than the number of right brackets over here. So now R of beta 1 S delta plus 1 I can replace as R of gamma. So I have shown that L of gamma is greater than equal to R of gamma. Have I answered your question?
Yes, ma'am.
Okay. Okay, so is it clear now? So basically what we showed, we have showed that for all three kinds of productions, if you look at the last step of derivation from S to alpha, if you look at the last step of derivation, this beta to alpha derivation, we analyze, okay, these are the three kinds of productions because of which the last step of derivation can happen. For each case, we have argued that if for beta conditions 1 and 2 hold, then for alpha conditions 1 and 2 also hold. And therefore, 2 also holds for alpha, and therefore, no matter which sentential form we are deriving from S, alpha is always going to be balanced. And therefore, if alpha is a sentence, then that is the balanced parenthesis string that has been derived, and therefore it is also balanced. Any questions regarding the first part? So we have shown that anything that is any string that is constructed by the grammar, that is derived by the grammar, is a balanced parentheses expression. Now we need to show the other way around, that any balanced parentheses expression can be derived by the grammar.
Madam, here we can take any prefix, right? Even though we wrote beta 1 as beta 2, we can take some part of beta 2, and as you took like delta as a prefix of beta, right?
But we need to argue for every prefix, not just any prefix. That's the reason why we analyze three cases. First is when it's a prefix of beta 1, next is when it's a prefix of beta 1 bracket S, and finally prefix of beta 1 S delta. Delta could be epsilon.
Okay, ma'am.
We need to argue, condition 2 was that you give me any prefix of X, the surplus function for that prefix should be greater than equal to 0. So that's what we needed to check. Okay, so I'm moving on to the second part. So what happens if X is balanced? I give you a string that is a balanced parentheses expression. Can I show that X can be derived from S using the grammar? So now we will be inducting on the length of X. And of course, if X is balanced, then X will satisfy 1 and 2. Now in the base case, if length of X is 0, that means X is epsilon. We have a production just to derive epsilon itself. So the base case is done. Now in the induction hypothesis, we are applying induction hypothesis and assuming that for anything less than, let's say, some length n, look at all strings of length less than n, they can be derived from S. This is the induction hypothesis. Now for some n, look at a string that is of length n. We will be concluding that that string can also be derived from S. There are two ways in which this string can be. Either there exists a proper prefix y of x that satisfies 1 and 2. We know that y satisfies 2. Either there is a proper prefix such that it satisfies 1 and 2, meaning that the number of left brackets in y is equal to the number of right brackets in y, and also like all prefixes of y will have positive surplus, or no such prefix exists. So intuitively you can understand that this is sort of this is the case where you have some alpha 1 alpha 2, x looks like alpha 1 alpha 2, and this is the case where x looks like bracket alpha. because this is the place where this I will consider as y, which satisfies 1 and 2. It should satisfy 1 and 2, right? Because this is also a complete balanced expression. Okay, so this is intuitive. Now let's go into the formal proof. So the first case is x is of the form yz. Z is not epsilon. Z is not the empty string because we are considering a proper prefix of x. If y satisfies 1 and 2 and x also satisfies 1 and 2, then it must be the case that z satisfies 1 and 2 as well. Please check this for yourself. Now that means look at y and look at z, both are of smaller length than x. So by induction hypothesis, I should be able to derive both y and z. Now then how do I derive x? I go in one step, I go from s to ss. Now the first s I use to derive y and the second s I use to derive z. And then yz is equal to x. Okay, in the first case, if I have a proper prefix that satisfies both 1 and 2, then I know how to derive x. Now the second case is what happens if there is no such proper prefix. That means x is of the form bracket z bracket. Okay, now another simple check is if x satisfies 1 and 2, so we need to verify that if x satisfies 1 and 2, then z does the same thing. Now from definition, z will satisfy 1. For 2, this is also simple argument. Look at all the prefixes of z. Okay, so look at lu. I want to consider lu minus ru, and I want to see whether this surplus function is greater than 0 or not, greater than equal to 0 or not. So I just say lu. Look at this. U is a prefix of z. Consider bracket u. This will be a prefix of x, right? But just structurally, if you consider structurally, u and bracket u will have a difference of bracket u will have one more left bracket than u itself. So lu can be replaced as l of bracket u minus 1, and ru is same as r of bracket u because I have not included any extra right brackets. So this expression can be written as L of bracket u minus 1 minus R of bracket u. Now the claim is that this will be greater than equal to 0. Why? Because we are in case B. In case B, L bracket u minus R of bracket u must be greater than equal to 1. Because otherwise, if not, that means L bracket u is a prefix of x. So L of bracket u minus R of bracket u is definitely greater than equal to 0 because x satisfies condition 2. So if L bracket u minus R bracket u is equal to 0, can you tell me what happens?
Lu minus ru will be less than 0.
Why?
Because in bracket u we are adding a left bracket but not a right bracket. So lu will be L bracket u minus 1.
Huh?
So
No,
then
no.
lu minus ru will be minus 1.
Yeah, okay, that is true. But I'm saying this is not possible in this particular case. See, if L bracket u minus R bracket u is equal to 0, consider this proper prefix bracket u of x. Over here, number of left brackets in bracket u is equal to number of right brackets in bracket u. Plus consider any prefix of bracket u. These are prefixes of x. That means for all of them, surplus is greater than equal to 0. That means bracket u is a proper prefix of x that satisfies both 1 and 2. Therefore, since we are in case B, it must be true that this condition 1 does not hold for bracket u. Condition 1 not holding for bracket u means that L bracket u minus R bracket u is at least 1. Is this point clear? And if L bracket U minus R bracket U is at least 1, that means that L, if I consider this expression, that means that L of U minus R of U is greater than or equal to 0. Is this point clear? Any questions? Okay. So we are so in case B, how do I derive X? I basically have to I know that if X satisfies 1 and 2, Z also satisfies conditions 1 and 2. So how do I do this? I know that if Z satisfies conditions 1 and 2, Z is a balanced parentheses expression. It is of length less than X. So by induction hypothesis, S can derive Z. Now, in order to derive X, this is what we will do. S in one step goes to bracket S bracket. Now, this particular S will derive Z. And now bracket Z bracket is X itself. So therefore, we have been able to derive X. So we basically can conclude now that any string that is a balanced parenthesis string can be derived. This is the exact set of strings that is derived by the grammar S going to SS bracket S epsilon. Therefore, we are done. So this was one formal way of I wanted you to look at least one example where you will see that many examples you will get the intuition of how to build the grammar from the structures of the strings. Here too, initially we built the grammar depending on the inductive definition of the language, but in order to prove it, this is how you have to formally show it. Okay, so let's move on to the next part of this lecture. I have 15 minutes, little bit more than 15 minutes. Okay, so we looked at context-free grammars, and basically we looked at the production. The main component of context-free grammars is the productions. How do we? These productions are basically the rules by which we are doing the derivations. So it would be nice if we had some structural properties of these productions. So for this is where normal forms of context-free grammars come in. We will be looking at some special forms of productions, or how to convert. You give me any set of productions. Is there an algorithm to make sure that each of these productions look a certain way? So these are called normal forms. The first form is the Chomsky normal form. This is where every production looks as one of the two forms. A going to BC, where A, B, C are all non-terminals, or A going to A, where A is a non-terminal and small a is a terminal. So either it will, you look at the right hand side, a non-terminal either derives to two non-terminals, concatenation of two non-terminals, or it derives to a terminal. So very simple structure. If I can get all productions of this form, it's a very simple structure. And there's also the Greibach normal form, where every production is of the form A going to A, B1 to BK, where capital A, B1 to BK are non-terminal non-terminal symbols, and this small a is a terminal symbol. So this B1 to BK, it is possible that BK is 0, which means that I just have A going to A kind of productions. So basically A going to A, or A going to A, B1, B2 up to BK, where K is greater than or equal to 1. These are the kinds of forms we have. So one thing to notice immediately is that there are no productions of the form A going to epsilon. Epsilon is not a string that you can generate from these normal forms. And another thing is you cannot have productions of the form A going to B. So these single productions, single non-terminal productions. Neither of the normal forms have this. So later on, you will also understand the significance of these normal forms. For now, they just simplify the structure. I know what to expect on the right hand side of any production if I am in a particular normal form. So any context-free grammar, for any context-free grammar G, we will be showing this, that for any context-free grammar G, there is a context-free grammar G dash in Chomsky normal form and also in Greeback normal form, another context-free grammar in Greeback normal form, such that if you just forget epsilon, the rest of the strings can be generated by this new normal form grammar. Okay, so you consider L of G minus epsilon. This particular language can be generated by a grammar G dash with some production rules in Chomsky normal form, and similarly by some grammar G double dash with some production rules in Greeback normal form. So can somebody tell me, if I have to get L of G itself, what is the extra thing that I have to do? For L of G minus epsilon, I have some normal form. What is the extra thing that I have to do in order to generate epsilon? So suppose G
it cannot be generated.
It cannot be generated in G dash. G dash generates L of G minus epsilon. If I wanted to generate epsilon, what will be the grammar? What will be the grammar for the full set? Suppose G dash has start state S dash. Yes, start state S dash. Start symbol S dash. So basically you can just add this S dash going to epsilon, an extra production like this, right? All other productions will be in some normal form, either Chomsky normal form or Greeback normal form. And there will be just one production that takes care of epsilon. Okay, so if you have Chomsky normal form for all the productions of LG minus epsilon, if I want to just generate epsilon, I also want to include epsilon, you just add this extra production and that would be enough. Every other production will be of the form that you want. Okay, this was just a side comment. Okay, now we will try to see what is the process of converting context-free grammars with any kind of production to those in normal form. And in particular, we will only be looking at Chomsky normal form in this course. Greeback normal form is a little bit more, like conversion to Greeback normal form is a little bit more involved. Chomsky normal form is good enough for us. So, and epsilon, what do we have to get rid of? We have to, in these normal forms, first and foremost, we cannot have epsilon productions, nor can we have unit productions. That is productions of the form A going to epsilon or A going to B, where B is also a non-terminal, single non-terminal. So these productions definitely have to be removed without changing the strings that are being generated other than epsilon itself. So we will be doing this in the following way. You consider any two productions. You do this exhaustively. This set of rules exhaustively. Apply this exhaustively. You consider two. You consider two productions. So basically, you're building a set P hat. You consider two productions of the form A going to alpha, B beta, and B going to epsilon, and then you add A going to alpha beta into this new production set P hat. So in the first step, you're only taking productions from P. In the first stage, you're taking productions from P and looking for pairs of productions of the form A going to alpha, B, beta, and B going to epsilon, and including a new production A going to alpha, beta. Similarly, if you find A going to B and B going to gamma, firstly, let's just look at the productions in P. If I find two such pairs, I'm going to add a new pair A going to gamma. So now I have some extra productions in P hat, let's call it 1. So P is equal to P hat 0. Then from P I added some new things, I got P hat 1. Now in P hat 1 again I will try to find such pairs, these kinds of pairs, and I'm going to build P hat 2. I keep doing this. At the end I will get P hat. So this will be the smallest set of productions that contains P and is closed under these two rules. Now obviously the question is, does this P hat basically is we keep adding new productions using the above rules on top of P, one step at a time. P will be P hat 0, then we go to P hat 1, then on P hat 1 we add some more production rules and keep doing this till it is closed. Okay. Can someone tell me whether P hat this is an algorithm that stops or not? P is a set of finite productions. Is P hat also going to be a set of finite productions, or can we just keep adding such things? What is going to happen? Is it possible that P hat contains infinitely many productions? What are the new kinds of productions that are being added? These are the left hand side is a non-terminal it's an original non-terminal. The right hand side is a substring or a subsequence of an existing right hand side from P. Right? Even if we go to later stages, we are only creating subsequences of an existing rule that was in P. So there were, if you consider the right hand sides that are available in P, that's finitely many. So the number of subsequences of the right hand side will also be finitely many. And therefore, this process will only lead up to finitely many productions, new productions. Therefore, each new right hand side is a subsequence of an old right hand side, and therefore P is finite. Since P is finite, P hat will also be finite. This process must end at some point. We will have tried all possible variations of non-terminals going to some substring gamma, subsequence of original original productions. So once I exhaust all these things, there is no other production to add anymore. I will be repeating myself. So therefore, if P is finite, then so is P hat. Okay, so now I will consider G hat to be the grammar where everything else is the same, number of non-terminals is the same, start point is the same, but the production set is now this P hat, which is the closed form, which is built from P, and it is closed under these two rules. If you notice the rules, basically we are trying to eliminate all these B's that led to epsilon epsilon derivations, and also these B's that led to we are also trying to get rid of this A going to B, where B is a single production. We are replacing this by A going to gamma. And if there was a B that was going to epsilon, we are replacing this by A going to alpha beta directly. Okay, so as P is a subset of P hat, then LG is a subset of LG hat. Now what about the other direction? LG hat is also a subset of LG, because look at any derivation, look at any step of derivation in using the new productions. That can be replaced by two steps of derivation if you consider the definition. You consider the definition by which you created this new production. You move back, you move backwards, and then you will end up in a set of old productions. So if you consider a new derivation, this would actually mean two so suppose this is P hat, this would mean two productions in P hat. Suppose P hat, this was P hat n, let's say. So this would mean two productions in P hat n minus 1. Similarly, that would mean a set of productions up to P. You can pull them back up to productions in P. But these are only finitely many. So whatever is derived in LG hat, you can derive using the productions of LG itself. You can use the productions of P itself to derive them. Therefore, LG hat is equal to LG. Now the claim is, if I take a minimum length derivation of x, x naught being an empty string, then this will not use an epsilon or a unit production in G hat. So then the implication is that from G hat I can get a G tilde where all the epsilon productions and the unit productions are deleted. Because I am preserving at least one minimum length, at least one derivation of x which does not use any epsilon or unit productions. So if I deleted all epsilon and unit productions from G hat to get a G tilde would still generate the same language without using any epsilon or unit productions. Let's prove this claim. So suppose for contradiction that there is a beta B going to epsilon derivation, B going to epsilon production that is being used in a minimum length derivation of S going to X. So that means, what is the structure? At some point I have derived gamma B delta, and then at some point I am replacing this B by epsilon to get gamma delta, which is then getting derived to X. And also it must be true that either gamma or delta, at least one of them should be non-null, because X is non-null. Okay, so then that means, how did I get to here? That means I have some derivation of this form that says S first goes to eta A theta, then in one step this production is applied to replace A by alpha B beta, and then again you continue your derivation to get to gamma B delta, after which in one step you replace B to B with epsilon, you get gamma delta and then X. But let's look at this thing. We have a new production in P hat that says A goes to alpha beta. So then I can create a shorter derivation where instead of taking this particular step, I can go from eta A theta, going to take this production and go to eta alpha beta theta, and then with n steps go to gamma delta and then again derive X. So I can bypass this particular I can bypass this particular production that I used by just simply using this new production, where instead of going from A to alpha B beta and then replacing B by epsilon, I can directly go from A to alpha beta and get a shorter derivation. Therefore, epsilon productions cannot be used in minimum length derivation. In the same way, you can show that unit productions cannot be used in minimum length derivations. That means that if I threw away all the epsilon and unit productions from G hat and obtain G tilde, then this would be a language that this would have L of G tilde would be same as L of G hat. Okay, so we got rid of epsilon and unit productions. Now we can concentrate on just getting whatever we have into the normal form. So we start with G tilde and we sort of modify the productions in the following way. So consider any terminal A in sigma. We introduce a new non-terminal A alpha and we introduce the production A alpha going to A. This is a new production we are including for each terminal A for each terminal symbol A. Now look at any existing production of the form which is not of the form B going to A. If it's of the form B going to A, I leave it because this is allowed in my Chomsky normal form. If it is of the form some B going to alpha A beta, then this B going to alpha A beta, then we will replace this by B going to alpha A alpha beta. Okay, so if a non-terminal was appearing on the right-hand side of some production, I will replace it. Sorry, if a terminal was appearing on the right-hand side of a production, I will replace this terminal by a non-terminal. This is possible. A non-terminal can appear because the right-hand side is a string from n union sigma star. This is possible, but I will replace this by A union A alpha. After this kind of exhaustive replacement, all productions will be of the form either A going to A or A going to a string of non-terminals. This will come from n star. There will be no terminals on the right hand side. Either there will be a single terminal or there will be no terminals on the right hand side. Now, so these are allowed, these are fine for us. Now, if you consider a production of this form, A going to a string from n star, we introduce a new non-terminal C, and this we can throw out and replace by A going to B1C and C going to B2, B3 up to Bk. And we keep performing this step until all the right hand sides of productions have length at most 2. So this will be done exhaustively. First this will be done, after at the end of which we will have productions only of the form only of these two forms. We leave productions of this form as they are. Productions of these form, the only problem is we have in Chomsky normal form there should be at most there should be exactly 2 non-terminals on the right hand side. We may have more than 2. If there are more than 2, we break them up basically into 2 such new productions, throw the old production out, so that at least one of them ends up being a production of the Chomsky normal form. The other one we will keep on working till I have a set of this will break into a set of new productions such that each of them have at exactly 2 non-terminals on its right hand side. So this is the process in which a conflict-free context-free grammar can be converted into a Chomsky normal form for all the non-empty strings. So here's an example. If you consider the balance parentheses problem, we had this particular grammar, but of course this is not in Chomsky normal form. If you consider Chomsky normal form, then it would look like this. Okay, you can try it on your own. And another example, A to the n, B to the n, we saw this example in the previous class. It would be of the productions will be of the form S going to ASB and epsilon. Again, not in Chomsky normal form. If I am looking for Chomsky normal form for all the non-empty strings in A to the n, B to the n, this would be A to the n, B to the n, where n is greater than or equal to 1. And then this is a Chomsky normal form for if you started with this set of productions. You can work out on your own how this is done. Okay, any questions? Okay, then we'll meet tomorrow again at 10 a.m. and we'll continue with context-free grammars.